Hi guys, welcome to 8.1 through 8.3 where we will be doing hypothesis testing. We're going to see how a formal hypothesis testing will allow for us to draw some statistically sound conclusions. So let's get started. What is a hypothesis? Well, it's kind of similar to what you had in science class when you reviewed the word hypothesis. It's a claim or a statement about a property of a population. Okay, my handwriting is a little shaky today, sorry. That says population over there. Now, a hypothesis test. This is the procedure for testing the claim or hypothesis about the property of the population. So we have a whole procedure for testing your hypothesis. The property of a population is going to be defined in some way. So we have a and we'll define the population parameter. So we will have some things like less than. And you may use either the word less than in your word problem. It could be the word less. It could be decreased. Anything that means going down, less than. Same thing with greater than. Again, you may instead see the word greater or increased. And of course, this one's pretty self-explanatory. Equals. That means they're the same. Okay, so we're going to look at our population parameter in regard to a sum property. All right, there are two types of hypotheses. We have the null hypothesis. You'll see a lot of stats jokes out here. The null hypothesis is H sub 0 or H naught. That's the null hypothesis, null meaning 0. Statement that the value of the population parameter is equal to some claimed value. Notice I said equal for the null hypothesis. Now the alternative hypothesis, which is H1, because it's not null, so it's got to be something else, so H1. You may see HA for alternative or H with a capital A for alternative. Again, some of those stats jokes will now make sense. Ho-ha, 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 H-O, H-A. Yeah, you're probably not laughing, guys, are you? And this one says that your parameter somewhat differs from the null hypothesis. And we will use, in this case, less than, greater than, or our favorite, not equal to. Remember, the null hypothesis is equal, and the alternative hypothesis uses one of these signs that's not an equal to. Okay, now a little bit more about the procedure. You're going to identify a claim and you're going to write it in symbolic form. So you're going to have like H naught equal to, or H naught is like something is equal to something, okay? Then you're going to identify the null and alternative hypothesis, and you're going to put those in symbolic form. So the alternative would be like H1 would be that same parameter is less than 0.50, okay? Then you're going to find a significance level, which is the probability used as the cutoff for determining when you're, significant evidence against the null. So for your significance level, which we usually denote that as alpha, it's the probability of correctly rejecting the null when it is false. And there's a lot of terms in here, so you're going to get used to some of these words along the way. They're going to sound kind of weird at first. Then we're going to identify our testing statistic to use the critical value method and find our values using the p-value method and go from there. So here's a little thing about notation. If you have a parameter that's a proportion of p, remember we did proportion, p, and mean, remember those parameters? Then you've got a normal distribution. If you've got a t, then you've got a t distribution. So this is the normal, which is the z-score. This one's the mean, that's a t. That's your t distribution. Here, your mean is mu, that means your z-score. Over here, this is your requirements that we had before. It has to be bigger than 5, and here's your z-score, your testing statistic. Here, when your sigma is not known, that's your t-score, and sigma is known, back to the z, and we never really did this guy down here. Okay, so you're good on that one. You didn't use any chi-squareds. Now back to our procedure. You're still going to go back and use that either the p-value method or the testing statistic, and you're going to go and either reject the null or fail to reject the null. These are the only two answers you're going to get: reject the null or fail to reject the null. So that's going to help us to determine if the null hypothesis, that claim, is true or not. Okay. That's probably making zero sense. You're going to see some stuff in a moment to make a little more sense. Now, testing for the critical value. There are 3 types of tests. There's the two-tailed test. That's when your alternate hypothesis has a not equal to, and then some value over here. Your parameter is not equal to some value. That means your critical region, so your critical region is in the extreme regions. That's there and there. Two-tailed. Not equal to is going to be both ends. A left-tailed, that's when your alternate hypothesis is less than some value. And that's going to be your critical region is the left region. So less than, okay? Then your next one, your right-tailed test, is when your alternate hypothesis is greater than some value. And remember, this means your critical region is the right region. Now, why does this matter? Well, you remember everything we did with those tables. If you're doing something and you're doing it from the tables, always go from the left. So this would be one where you'd have two tails. So you could go from the left and then subtract out to get the others. And remember, you have to have double because there's 2 parts to this. Again, this one would be going from the left. Well, that would be the left right there. Okay. And again, going from the left, but you've got the right, so you'd have to subtract to get that. So I'm just kind of giving you the idea of how we use those. And that's with the p-value. There are 3 types of tests for the p-value and the right-tailed test method. Your critical region in the left tail is the area to the left. of your statistic. Again, the right, that's area to the right. And 2 tells, again, since you got 1 at each end, that's twice the area beyond the statistic. Okay, we got some nice pictures down here. If we've got our test statistic here, then our p-value is going to be that area over there, that critical region to the left. If we've got the right, that's this one. And if we've got both sides, we've got 2 areas to consider. Now, here's a common thing. Don't confuse your p-value with the parameter p or the statistic p hat. Yep, we got a lot of p's in statistics. Number 7. Now comes the conclusion. We've already done the testing. Now we're to the conclusion. We will never use this word here, accepting the null. We're either, remember I told you, rejecting or failing to reject the null. So these are, you might want to make sure you have this table down because you need to know how you're going to say what you have. If your original claim does not include equality and you reject H naught, so it does not include equality, and you reject H naught, then there's sufficient evidence, this is how you would say it, there is sufficient evidence to support the claim, and then you put your original claim. If your original claim does not include, but you fail to reject the null, then there is not sufficient evidence to support, and then you put your claim. Now, if your original claim includes equality and you reject the null, then there is sufficient evidence to warrant rejection of your claim. And the last one, if your original claim includes equality and you fail to reject, then there is not sufficient evidence to warrant rejection and then your original claim. This is how we officially word things, so make sure that your condition, conclusion, you write this table down somewhere because you're going to use these fancy words. And then we will talk about our confidence interval. And again, we have for our one-tailed test and our two-tailed test and our alphas over here. Remember, a one-tailed test versus a two-tailed test, you can see how the alpha varies because you have 2 points at the end. All right, now something about equivalent methods. We're going to be looking at these confidence intervals for means and proportions and standard deviation, but we also need to know if using a confidence interval is equivalent to a hypothesis test. So here's a way to figure that out. Is your proportion, is your parameter, then no, it's not equivalent. If it's the mean or standard deviation, then yes. And we never use this one, so it's either no or yes. Proportion for your parameter, then no. Mean, yes. And we're going to do this in a little bit so you'll be able to practice this. Again, very large samples, they could result in small p-values, so it doesn't make much of a difference. So just kind of letting you know, but there are some errors that can occur. Type 1 and type 2 errors. If you reject H naught, but H naught is actually true, that's a type 1 error. Of course, if it's actually false, then yay, correct decision. If you fail to reject H naught, but it's actually true, then good, you got the correct decision. If not, it's a type 2 error. Okay, it's just giving you an idea of what those mean. Now, let's practice this step because there's a whole lot there. So first thing we're going to do is practicing figuring out what the null hypothesis is and what the claim is. So in part A, we'll express the original claim in symbolic form, and B, identify the null and alternative hypotheses. That's all we're going to do from a word problem. So most adults would erase all their personal information online if they could. A GFI software survey of 565 randomly selected adults showed 59% of them would erase their data, okay? So our original claim is that 59% or most adults, so most would be greater than 50%, would erase their personal online information. This is our claim. Now, our H0, I told you the null hypothesis is always equal to. So, P equals 0.50. That's our null hypothesis. And since our claim is, we said most, that's greater than, so our H1 or our alternative hypothesis is P is greater than 0.50. Okay, let's try a couple more, just make sure we get this. Cell phones. The claim is fewer than 95% of adults have a cell phone. That's our original claim. So, fewer than 95% have a cell phone. In a study of 1128 adults, 87% said they have a cell phone. Okay, so our null hypothesis is equal to 0.95, and our alternative hypothesis is less than 0.95 because our claim used that. Now to our next one. The claim, the mean pulse rate of adult males is equal to 69 beats per minute. Okay, so our claim, and that says mean, you notice that? So mean is mu, and it says is equal to 69 beats per minute. So our null hypothesis, remember it's always equal to, and so our alternate must be not equal to. Okay. Now, example 4, we have the test statistic Z is 1.00 is obtained when testing the claim that P is greater than 0.3. First, we're going to identify the hypothesis test. Is it two-tailed, left-tailed, or right-tailed? Then we're going to find the p-value, and then we're going to use the significance level to tell us if we should reject the null or fail to reject it, okay? So first things first, we have Z equals 1.0 is obtained when testing the claim that P is greater than 0.3. Greater than, it says greater than, suggests that our answer is right-tailed. And again, that's because of the greater than sign. Okay. Now we're going to find the p-value. This is what you would use in your calculator. Since it's on the right, and this is a Z statistic, we're going to use 1 minus the normal cumulative distribution. And remember, we always put in a small number, because that's how our calculators work. We're going to put in the statistic of 1 from right here. And then, of course, it's normal, so 0, 1. And in this case, I get 0.1587, okay? That's my p-value. Now my next one. Using a significance level, alpha is going to be 0.05. Should we reject or fail to reject the null? So our answer of our p-value was 0.587. And is he greater than 0.05, which is our alpha? Yeah. Since it is greater, this is true. So we must, fail to reject the null. So this is our answer, fail to reject the null. Because it is true. We're failing to reject, and though we never say it, we're basically saying that the null is true. Okay, let's go to example 5. Get a good grip on this. This one says our test statistic is z equals negative 2.50, and it's obtained when testing the claim that p is less than 0.75. Ooh, less than. Less than is going to mean left-tailed, okay? And if it's left-tailed, that means all our area is on the left, and this is a z, so it's normal. So we're going to use the normal cumulative distribution. And again, we put in a small number. And then we put in our z testing statistics, so negative 2.50, and our 0, 1 because of the mean and standard deviation. And we get that our p-value is 0.0062. Okay. Now we're going to go and look at our alpha is 0.05. So 0.0062, that's our p-value. Is he less than 0.05? The answer is yes. So, since this is true, we must reject the null. All right. Let's move to our next one. Our testing statistic, Z 2.01, is obtained when testing this claim, P does not equal to 0.345. So not equal to means two-tailed. To find the p-value, we're going to have to do 2 times the normal cumulative distribution. Why 2 times? Because we have 2 tails. Our statistic is at 2.01 all the way up to a big number, and then 0, 1, and that's going to give us 0.0444 for our p-value. And now we're going to look at our alpha is 0.05. So 0.0444 does not equal, Let's see if he's less than 0.05. I don't know why I put not equal to. 0.04 compared to 0.05, he's less, so we must reject the null. Okay. Our next one, our statistic Z, and we're claiming P is greater than 0.3. So our critical value, we didn't talk about that before. What's critical value? Remember, that's alpha. And we usually make him 0.05. So how does that mean? We're going to go and do the inverse norm, because it's a Z, so normal, inverse normal of the area, 0.95, because 1 minus 0.05 is the area of 0.95 from 0 to 1. And that is a critical value of 1.645. So there's our critical value. And it says reject or fail to reject. Well, how do we figure that out? Well, it's a normal CDF because of the Z, and it's greater than so we can find negative 9, 9, 9, 9, 9, and 9 to our 1.0, and from 0 and 1, and that'll tell us that our area is 0.8413, And is this greater than 0.05? That's our alpha. And it is, so must fail to reject the null. All right, so all we've done is find our claim, turn it into our null and alternative hypothesis, and then we've determined, is it going to be a left, right, or two-tailed test, found p-values, and figured out how do we do rejecting or failing to rejecting the null. Now, that's not all we have to do, but that's what we're getting at. So now we're going to talk about testing a claim about a proportion. And so this one is similar to what we saw before. As far as notation, we've got n for the sample size, p hat is x over n for the sample proportion. P is the population proportion, and Q is 1 minus P. There's still requirements. It has to be a random sample. Binomial distribution has to be satisfied. That's the bins. And we want to have n times P greater than equal to 5 and n times Q greater than equal to 5. Those have to be satisfied as well. So, and if that is, then we can approximate with a normal distribution, but that means mu is n times P and sigma is the square root of n, P, and Q, which we've seen before. Now a little bit more. The testing statistic is still Z, and that's how to find him there. And you can still use your p-values from your table or the calculator, which I've been using the calculator. And you can see how you do that there. Now, some equivalent methods. You can test claims about proportions. Your confidence interval method is not equivalent to a p-value and critical value methods, and it could lead to a different conclusion. Okay. Now, let's get to some examples so you can see what you're doing. This says a study of sleepwalking or nocturnal wandering was described, and it included information that 29.2% of 19,136 American adults have sleepwalked. What is the actual number of adults who have sleepwalked? Okay, this has no, this is not really all that much statistics. This part is just basic math. Find the number of successes. So that's 0.292. That's the 29.2% times, we had 19,136 adults, means that we get 5587.712. So 5588 people, because you can't have 0.712 of a people. All right, example 2. Using this data that we had on example 1, would we be justified in stating that fewer than 30% of adults have sleepwalked? And we need to use the 0.05 significance level to test the claim that it's less than 30 or 0.30. So we got to check our requirements. Simple random sample, which, yep, it's random. Sorry, I am real shaky today, so my handwriting is terrible, guys. Now, the bins, is it a fixed number of trials? Because our adults are 19136 adults. Does it have independent trials? Yeah. What you do in your house doesn't affect mine. There are 2 categories. Either you sleepwalk or you don't sleepwalk. Okay? And is our probability constant? So probability of success constant. And we got that as 0.30. And then we're going to check n times p, is that greater than or equal to 5? N times q, is that greater than or equal to 5? So we take 19136 times 0.30, which, yes, that's greater than or equal to 5. And we take 19136 times 0.70, and is it greater than or equal to 5? So yes. Now I'm going to write the claim in symbolic form. We're claiming those that have sleepwalked are less than 0.30. And then the opposite of that claim would be greater than 0.30, greater than equal to, sorry. All right, now part D says we want our H naught. Remember, that is always equal to. So this one would be, remember, our less than is what we're trying to find, 0.30. Our significance level, they told us that, alpha is 0.05. Now, to do a prop Z test to find the p-value, and you can use your calculator for this, you go to stat, over to test, and I believe it's choice 5 that you'll choose. And for P naught, that is 0.3. For X, that is 5588 people. In 19136 population, your prop is going to be less than, and then you'll of course calculate, and it'll tell you some information. It'll tell you the P, and it'll tell you the Z score at the same time. So in this case, from this, running that, you get P is 0.008. Okay. Now we're going to interpret the p-value. 0.008, is that less than 0.05? Yes, it is. Since it is, we will reject the null. That means we have evidence for the alternate hypothesis. Okay. And then using the critical value method, we have our our test statistic Z. There we go. See if I can say that. P hat, in this case, which is 0.292. That was the population percent they give us, minus P, which is 0.30, over the square root. P is 0.3, Q is 0.7 over N, that's 19136. We figure that out, and he is negative 2.41, which we also would have gotten from here too. It would have given that Z for us as well. What kind of test did we use? We used a 1 prop Z test. And our critical value, which we found that earlier, or we can find that earlier, or now, I'm sorry. The critical value, to find that, remember we have a 95% confidence interval, so that means A is 0.05. So if we do Z is the inverse norm, and that's of 0.05. Oh, I need to choose the right, sorry about that. there's my 1. And then I'm going to put the word right in there. When we type that into the calculator, we get about 1.6448 something. So that's 1.645. That's our critical value. So here's a little graphic at the bottom. Our critical value was at 1.645. We will reject, we will fail to reject right here in the middle between positive and negative critical value, and we will reject anything above or below. Now, ours was at critical value negative 2.41. Since that's way below, then that's why we rejected the null. Okay, let's look some more. Now, using the confidence interval method, we use 90% since it's left-tailed. That was a slide I gave you earlier about the confidence interval. And so we would use the 90% confidence level to get the interval. In this case, how do we get this interval? Well, it's x bar plus, plus or minus the error. That's what mu is. So in this case, I get 0.292 plus or minus 0.005, and that's going to give me a confidence interval of 0.287 to 0.297. That's what we get right there. Now this one's about fast food drive-through orders. McDonald's has 33 orders that are not accurate among 362 orders observed using a 0.05 significance level. Okay, so we're going to do this again. Null hypothesis. That means it says equal to 10%. So P equals 0.10. Our alternate is P does not equal 0.10. The test statistic, we have P hat. Okay, so P hat is 33 out of 362. This is where I got those numbers, which is 0.0911 something. So 0.091. So 0.091 minus P, just 0.10, over the square root. That's 0.10, 0.90 out of 362. Type that in the calculator, and we get Z is negative 0.5606. Now to find the p-value, we do the prop test, and we put that in. With that, it gives us 0.5751, and it also confirmed that our Z is negative 0.5606. Now to find the critical value, then we do, for the critical value, that's this, Z is the inverse norm, and it's 0.05, 0, 1 on the right side, and it's 1.645 again. And then, so our conclusion, let's go to him. So our conclusion, we got 0.5751, and that is greater than 0.05. So we are going to fail to reject the null since it's greater. All right, now 8.3, we're going to test a claim about a mean. All right, we finally made it to 8.3. So let's go to him. Notation we need. N is the sample size. S is the standard deviation of the sample. X bar is the sample mean. And mu bar is the population mean. There have to be requirements. There has to be a simple random sample. And the population is normally distributed with N greater than 30. We will use the test statistic for the T here. We have about p-values and critical values using our table again, but remember we're using the T distribution, so don't forget about that. All right, so we have here the data for, it looks like some randomly selected adult subjects, okay? They tell us the N, the X bar, and the S. They say between 7 and 9 hours is what we should sleep. We are going to use the p-value method with a 0.05 significance level to test the claim that the mean amount of sleep is less than 7 hours. So here's our data. All right, now we're going to see if any requirements were met. Yes, we have the simple random sample. And we see that it, from our histogram, that it looks normal. Ish. And so we met the requirements. Now H naught, that's our mu. And we said 7 hours of sleep, so equals, always go here. Mu less than 7 is our alternate hypothesis. Since we had 0.05 for that, we're going to go back to this. They gave us our X bar, so that's 0.6, oh, sorry, 6.8, 1, 2, 3, 4, 5, 6, 7, I think that was 7 threes on that, minus the 7 that we want, over, and they gave us this one, the standard deviation of 1.99240984 over the square root of n. N is 12. And we pop that in the calculator and we get the T to be negative 0.290. Now we're going to continue our example. So we're going to go and do, again, this is the steps in the calculator. Stat over to test, and you're going to choose number 2. It's the T test. Why? Because this is a T. And you're going to put input is your stats, and then your mu naught is 7. Your X bar is 6.833, you get the idea. Your SX is 1.992, you get the idea. N is 12, and you're going to put mu is less than mu naught as your choice, and then calculate. And what this should tell you is that your T was negative 0.28. I cannot write today. Negative 0.28977 and so forth. And that your P is 0.3886, that kind of thing. So what we care is your P, which is 0.3887, is that greater than 0.05? And it is, so we fail to reject the null. And we conclude not enough information to support the claim. And the claim was that mean sleep is less than 7 hours. All right, now on to number 2. What's the critical value? We just found that. That was T. Wow, me and my writing today. T is negative 0.290. Now, testing our claim, there's a standard deviation is known. There's our formula. All right, airport data speeds. Let's see what we know. We know the mean, we know the sample size, and we know the testing statistic. It wants the p-value. Using the calculator, it's second vars and number 6. And what we do is we put in the t cumulative distribution, put in a small number, and that's negative 1.625. That's what they gave us. And 12, because the degrees of freedom is 1 less than your n, and that's going to equal 0.065 something. And it's two-tailed, so times 2 equals 0.1301. Okay, our next one, body temperature. We got the claim that for a 12 a.m. body temperature, the mu, the sample size, and the test statistic. So again, back to second vars number 6, and we're going to do the t cumulative distribution for a small number. They give us negative 2.503. The degrees of freedom, 4 minus 1 is 3, and in this case we get 0.0437. And of course that's rounded. This one, mu, sample size, test statistic. So again, your T, CDF, and this one, 1.340 to a big number, comma, 6 minus 1 is 5. And that tells us about 0.11896 times 2 sides. So this one's about 0.2379. So we did our p-value on these. Okay, a little bit more practice. But their airport data speeds, our H naught was our mu equals 4. And that's right here, mean less than 4. And our mu less than 4. Our statistic, it's going to be 0.05 for our level here. Test statistic T, well, we can tell that from the screenshot. It says negative 3.66. And our p-value, our p from that same screenshot, right underneath it, 0.3579. So our conclusion is that we are going to fail to reject the null. And why is that? Because P is 0.3579, and that is greater than 0.05. All right, I think that leaves you at the end. You're welcome to try this one as practice. And now you're going to work all these in Chapter 8, hypothesis testing. Good luck, boys.